Okay, we are back at it now with lesson 8.5. So we're going to be talking about trapezoids, isosceles trapezoids, and kites, all in lesson 8.5. The first video is just going to focus on trapezoids right here. So I'm going to put 8.5 up at the top. Alright, and then we're going to start talking about things. So start once again with our definition. Okay, so a trapezoid. What makes a trapezoid a trapezoid? Now, there is some disagreement on this. This is one of those things where some mathematicians still have some disagreement, but we're going to go with what's in our book, and it's what I actually kind of go with. I'll explain to you the other one real quickly, but we're going to define a trapezoid as a quadrilateral with exactly one set of parallel sides. And obviously if they're parallel, they're going to be across from each other. They cannot intersect each other. Okay, exactly one set of parallel sides. Okay, and we call those sides the bases. Okay, so there's two different bases. They're actually going to be different lengths. We'll talk about why in a little bit here. Okay, so let's draw an example. So maybe something like this, where we have the top and bottom parallel. Okay, or it could be maybe something like this. Where in this case it's the left and right that are parallel. Okay, so we could have either one. Now, you're not going to have this side and this side be parallel as well, because it says exactly one set. Or in this case, you're not going to have the top and the bottom be parallel. All right, also the bases cannot be equal to each other. Right, if the bases are the parallel sides, they cannot be equal, because we had a theorem back in lesson 8.3 that said if one set of opposite sides was both parallel and congruent, then the shape had to be a parallelogram. So if these bases, the parallel sides, were also congruent, then this would be a parallelogram. And a parallelogram, by definition, has two sets of parallel sides. And when we say exactly one set, we're saying it can't have that second set. Now, some mathematicians do believe, or their definition would say that a trapezoid is a quadrilateral with a set of parallel sides, and it could have two sets. So under that definition, every single parallelogram is automatically considered a trapezoid. Okay? Trapezoids can become parallelograms, all right, but they don't have to be. Every single parallelogram would have to be a trapezoid. Our book completely separates the two. If it's a trapezoid, it cannot be a parallelogram, okay, because this has two sets of parallel sides and this has exactly one. And if it's a parallelogram, it can't be a trapezoid. So we're going to go with that definition. And I know there are some people out there who disagree with that, and probably some textbooks that disagree with that as well. All right, remember, we're going to do sides, angles, and diagonals, and then we're going to get down into the other. The most it's kind of the biggest time in this one is actually going to be spent in the other, because there's something special that happens down there. All right, let's talk about sides. So getting out our thing here. All right, looking at our different things for sides. So opposite sides are parallel. Well, that was part of the definition, so yes. But it's only going to be one set. So we're going to put A1. All right, so A1. All right, by definition, A1. Kind of makes you hungry for steak or something, right? Okay, A1 by definition. All right, okay, let's look at the next one. Opposite sides are congruent. Two sets or one set. Well, we already said that these sides cannot be congruent. So the question is, what about these sides? Maybe, yeah, they could be, but they don't have to be. And since they don't have to be, we're not going to write it down here. Okay, next thing under sides. All sides are congruent. Nope. That's definitely not true. Consecutive sides are congruent. Four sets or two sets. Okay, so consecutive would be like the top and the left. Do they have to be congruent? No. Is it possible that they could be congruent? Yes, but we're not going to write down things that are only possible, because these are things that have to be true all the time. So that's it. That was easy for sides. All right, let's look at angles. Okay, so that's our next thing over here is angles. All right, so let's come back over here. All right, first thing for angles. Opposite angles are congruent. Okay, opposite angles are congruent. Well, that looks really, really obtuse, and we don't really go by looks, but sometimes looks help you determine whether or not it's even worth trying to prove. These are almost more like right angles. There's just no way to prove that those are going to be congruent. If you think back to when we proved that they were congruent for parallelograms, okay, we drew a diagonal, All right, we got some congruent angles by alternate interior angle theorem, but we did that twice. All right, and then we had the reflexive property. Well, when we try to use alternate interior angle theorem here, we can only do it once. Okay, we can't do it twice. All right, so let me show you real quick what that would look like. So if we try to prove in some kind of parallelogram that we have congruent triangles, basically. So we've got parallel on the top and the bottom. If I draw this diagonal, these angles are congruent by alternate interior, and this is congruent to itself by reflexive property. But these sides, top and bottom, aren't congruent. This angle here is not congruent to that angle there because these sides aren't parallel. So all we have is angle side. That's not enough to prove we have congruent triangles. So we can't get these opposite angles congruent by CP, CTC, or anything like that. So this isn't going to work. So we do not have opposite congruent angles. Okay? Well, let's look at what the next thing says for angles. All right? It says consecutive angles are supplementary. 4 sets or 2 sets. Okay, well, let's look back at a picture again of a trapezoid. Okay, something like this, where we've got some parallel sides. Okay, well, we learned this quite a while ago. Let's say we extend this out here, we extend this out here, we extend this out here, and we extend this out here, and I just kind of cover up this section here. All right, we got parallel lines, we got a transversal. Remember that this angle right here and this angle right here are consecutive interior angles. They're in between the parallel lines, are on the same side of the transversal. So we learned way back in a previous chapter that these were supplementary. Okay, we could do the same thing over on this side. We could extend this transversal out. Okay, we could extend our parallel lines out. All right, once again, this angle, I'm going to put 3 marks because it's different than these two over here. And for this one, I'll put kind of a different mark, okay, 1 but with a little mark on it. Well, these are also supplementary. Okay, once again, consecutive interior angle theorem. Now, because the left and right aren't parallel, we cannot do that for here and here. We can't say they're supplementary like we did for parallelograms. So we only have 2 sets. Okay, we only have 2 sets. All right, so angles, consecutive angles are supplementary. That was letter B. All right, but it's only 2 sets. We're going to go B, 2, and it is a theorem. All right. It's a previous theorem. I don't even remember what chapter it was in or anything like that. So it's theorem, and if you want to just jot yourself a little note, it's the consecutive interior angle theorem. Okay, if you want to actually look it up in your book or something, that's fine. Figure out what theorem number it is. I don't really care, but I'm not going to let you put theorem numbers in your homework anyways. All right, next. All angles are congruent. Well, that's definitely not true. Consecutive angles are congruent. Okay? Well, we just talked about, coming back to here, that these angles are supplementary. Now, is it possible that they could be congruent? Yeah, if they were both 90 maybe. That'd be the only way. 90 plus 90 is 180. Okay, so that's possible. Well, what about these two? Could they be congruent? Yeah, if our shape looked a little bit different, we're going to talk about this in another video here, but if we get this kind of trapezoid here, okay, then we are going to have congruent angles here and here. And then we're also going to have congruent angles here and here. Okay, so we're going to deal with this kind of shape later on. It's a special kind of trapezoid. Okay, but it doesn't have to be true. All right, we can tell here that these angles aren't really congruent. They're not even close. It's not worth trying to figure out. Okay, so we don't have to have consecutive congruent angles. All right, well that's it there. Diagonals. Okay, diagonals bisect each other. No, cannot be true. It's not one of those where it could be true, maybe, maybe not. It cannot be true because if both diagonals bisect each other, then it has to be a parallelogram. That was one of our theorems back in lesson 8.3, so there's no way that's going to happen. Okay? Diagonals are congruent to each other. All right? Again, this is one of those where we can just kind of draw a picture, take a look at it, and see if it even makes sense that it might be true. So let's draw a picture here. Okay? So something like that. Okay, so I got my parallel marks. Okay, and I've got this diagonal, and I've got this diagonal. Okay, so we've got this, and if I kind of turn that without moving my fingers, you can tell I'm extremely short over here, not even close to being congruent. So that distance there, okay, that distance matches up. But there's no way that it's even close. All right, we could even show you it almost more this way. Okay, it's very obvious. Okay, if we do something like this, is there any way that this diagonal here is going to be congruent to that diagonal that goes all the way down there? No, that doesn't make any sense at all. Okay, so that does not need to be true for diagonals. Okay, next one, diagonals are perpendicular to each other. Well, use the ones we just drew. Does that look like a right angle at all? That looks acute, that looks obtuse, it's not even close, it's not worth trying to prove. What about this one? No, that's going to be the acute one over here, that's going to be obtuse. Okay, we could even make other examples that are more obvious than this, but they're not going to be perpendicular to each other. Is it possible they could be? Yeah, maybe. Alright, but usually they are not. Okay, diagonals bisect opposite angles, 2 sets or 1 set. Okay, that means that as this diagonal runs up into the corner, that this angle right here would have to be congruent to this angle right here. Well, it's pretty obvious that's not even close. Okay, well, what about, like, you know, here, let's look at another one. What about here? This congruent to this? Yeah, that might be true. I don't know. It's possible. Okay, but if it's possible but not required, we're not going to put it down. That's it. That's it for diagonals. Well, none of them were absolutely had to be true. So what we're going to do, just so we realize you know, not that you didn't fall asleep during the video or whatever, forgot to take notes, we're actually going to put a big X through this box to show that it's completely empty. It's the easiest box on the whole chart. There's nothing in it. Okay, there's nothing true about the diagonals of a trapezoid. Okay, let's go down to other. Okay, let's look at these things. Base times height. That doesn't work very well because the bases are different lengths. Okay, so we can't just, well, which base would we pick? I don't know. So we can't use this. Length times width. Well, the length of a trapezoid is not perpendicular to the width of the trapezoid. Remember, the things we multiply need to be perpendicular in order for this to work. Okay, diagonal 1 times diagonal 2 over 2. That's not going to work. The diagonals are not perpendicular to each other. Side times side, or side squared. Well, the sides don't have to be equal. Okay, height times base 1 plus base 2 over 2. Hey, now this, we haven't talked about this one yet, any of this, because all the other times our bases were the same, but now the bases are different, so we do have 2 different bases. All right, this is the formula for the area of a trapezoid. We take the height times parentheses, base 1 plus base 2, all divided by 2. Okay, so that's letter E, so we're going to put that right here, letter E. Okay, that's important. Now, if you look off to the side, height times the average of the bases. Now, once again, the base and the height have to meet at a right angle. So let me show you what that looks like. All right, so here we go. So I've got some kind of trapezoid. All right, maybe something like this. And I put a bunch of different distances on this, and you got to know which ones to pick. So let's say that these are our parallel sides. Okay, and I tell you that this is 17. And this is 9, and this is, I don't know, it looks like maybe about 8, and this is 11, and I'm going to put this in here, make a little mark here, and I'm going to tell you that that is 7. Okay, well, how in the world do I know? Okay, here we go. Remember, the bases are parallel. So this is base number 1 and base number 2. If you call this base 1 and base 2, it's okay. It doesn't really matter. It'd just be like turning the shape upside down. So this is base 1. This is base 2. Okay, which of these things is my height? Remember, base and height have to meet at a right angle. Okay, so I see a right angle mark here. That's where the 17 meets the 7. Well, what about up here? Is there a right angle mark? Yeah, we actually had a theorem a while ago that said if 2 lines are parallel and a transversal is perpendicular to one of them, it's also perpendicular to the other one. I think it was called the perpendicular transversal theorem. So this is also perpendicular up here. So my formula says height, 7, times base 1, 17, plus base 2, which was the 9, divided by 2. Okay, I'm going to zoom out just a little bit so you can see all of that at the same time, both the picture and the formula. Okay, there you go. Okay, you can see how all that works. Okay, height, base 1, base 2. Well, what about this 8 and this 11? They don't matter for area. Okay, they just don't matter. All right, so here's our formula. So 7 times 26 divided by 2. 7 times 26 is 182 divided by 2. And that gives me 91. and then we label it with units squared or inches squared or feet squared. Since they didn't give us one, we're going to just go ahead and use units. So 91 units squared. All right, so that's the formula for area of a trapezoid. Now let me give you one more example of that. So sometimes, all right, they may not give you, or it may not seem like they give you enough information, but they do. Okay, so let me show you what I mean by that. So let's say they have something like this. Okay, and this time one of the sides is actually perpendicular. We didn't have that in the last one. Okay, and let's say that they tell you this right here is, oh, I don't know, let's come up with some good numbers. Let's say this is 29, and this is 35, and this is 14. Okay, it looks like a 19. Sorry if it looks like a 19, it's a 14. Okay, so let me zoom in a little bit here so you can see that a little bit better. Okay, now, how in the world do I find this distance over here? Okay, well, what we do is we can draw a dotted line straight up and down here as well. Okay, we know that's perpendicular. There has to exist some line that's perpendicular, okay? Now that takes this 35 and it kind of splits it up. It doesn't necessarily split it evenly, but what we've created here is a little rectangle. Kind of looks like a square. It might be, it might not be, it doesn't matter. It's definitely a rectangle. It's got right angles everywhere. So that means if this is 14, this is also 14 right here. Okay, and 35, the whole thing, minus the 14 leaves me with 21. 35 minus 14 is 21. So 35 goes the whole way. 14 and 21 are how it gets split. Okay, well, let's call this right here x. Well, how in the world do we solve for x? Hopefully by now you remember we've got a right triangle, we got a missing side, we got to use the Pythagorean theorem. Keep in mind that which one is a, b, and c. This is c, it's the hypotenuse. Okay, so x squared plus 21 squared equals 29 squared. Okay, now we're going to do some math. X squared plus 441 equals 841. We subtract the 441. X squared equals 400. Take the square root of both sides, and x equals 20. Well, that's not the answer. Remember that I was just trying to figure out some stuff. So this is 20. Well, that means this over here is also 20. And now I can find the area. Okay, remember area was base 1. Base 1 is 35 plus base 2 is 14. Put that in parentheses. Times the 20. Okay, so let me shift over here so you can see what that looks like. Height, parentheses, base 1 plus base 2. Those parentheses are important because we're not just going to multiply this and get 700 and then add the 14. Okay, we're going to do inside the parentheses first. Okay, and remember all of that is divided by 2. So 35 plus 14 is 49. Now some of you might say, well, can I reduce right here right now? Yeah, you could. Okay, you don't reduce here as well though. Okay, just reduce once. Or you can just multiply 980 over 2. And 980 over 2 equals 490. And this could be inches squared, feet squared, meters squared, whatever. I didn't give you a label, so we're calling them units if we didn't give you a label. So 490 units squared. Okay, so hopefully you understand how that works. Now the last thing, okay, down in this other section is not F, mixed between a rectangle and a rhombus. Remember, that's a square. Okay, but G. The mid-segment is parallel to the two bases and equals half their sum. Or in other words, their average, half their sum. Sum means addition. So if I add two things and take half of that, that's averaging. Okay, mid-segment is parallel to the two bases and equals half their sum. That's a true statement. That's letter G. And by the way, that is the mid-segment theorem. That's my abbreviation for theorem for trapezoids. Okay, mid-segment theorem for trapezoids. We had a mid-segment theorem for triangles earlier. Now we have one for trapezoids. So this is the end of the trapezoid thing. So let me just show you how this mid-segment theorem works, and then we'll be done with trapezoids. We'll do isosceles trapezoids next one. So if I draw my trapezoid here, I'm going to give you some terms. Okay. So let's make sure we get all these terms figured out. Okay, so got my parallel pieces. Zoom out just a tad so we can get all this in here. Okay, so remember we called this base 1, and this was base 2. Okay, this side over here is called a leg. This side is another leg. The legs may be equal, they may not be equal. Okay, it just kind of depends. All right. Height we already had, where we drew straight up and down, perpendicular. I'm not going to draw that in here, but I'm going to draw a mid-segment. A mid-segment, just like we did in triangles, a mid-segment goes from the middle of one side to the middle of another side. Now, specifically which sides? It's the legs. So if I take this midpoint, make those equal, and I take the midpoint over here, and I make those equal, but they're not necessarily equal to these over here. And I'm going to draw this. I'm going to draw it as a dotted line for right now. Okay, that thing right there is called the mid-segment. Okay. Now, just like a mid-segment of a triangle, remember, a mid-segment of a triangle was parallel to the side that it did not intersect and half of that side's length. Well, this is going to be parallel to the two sides it doesn't intersect. Okay, so I'm going to go ahead and put this mark on here, parallel. And instead of saying half its length, okay, because we don't really have one base that it's half of. It's actually smaller than this one, but it's bigger than that one. So instead of saying half of its length, we say half of their lengths put together, their sum, their average. Okay, so this is what it would look like in a picture. So we got something like this. We've got these equal. Okay, we come over here, we've got these equal. Okay, and they tell me this is 9 and x and 15. Okay, so x, the mid-segment, is means equals in math class, half. Okay, half means I'm going to divide by 2. Half their sum. Sum means I'm going to add. Well, 9 plus 15 is 24. Over 2 is 12. So it's 12 feet or inches or units. Okay, then we can do a slightly different version of that. Okay, let's say we have something like this. Okay, once again we've got the congruent, so I know that's a midpoint. Got congruent here, so I know it's a midpoint. Okay, let's call this x. And let's call this 14. And let's call this, I don't know, 22. Okay, well, the mid-segment, 14, is half. Half means we divide by 2. The base's sum. Well, how do I write that? Sum means I add. Well, I add the bases, x plus 22. So this is a little bit hard to figure out. I can't just do math. Okay, x was already all by itself over here. So here I just did some math. I added and divided. Here I've got to do some algebra. So I'm going to put this over 1 so that I can cross multiply. 1 times that doesn't change anything. But 14 times 2 is 28. I subtract 22, and I get x equals 6. And we can check that, see if it makes sense. 6 plus 22 is 28. Cut the 28 in half, we get 14. It makes sense. Okay, so that's the mid-segment theorem for trapezoids. And keep in mind, the mid-segment theorem also says that these three things are all parallel. The bases are parallel by the definition, and this mid-segment is parallel by the mid-segment theorem for trapezoids. Okay, so all three of those would be parallel to each other. Last thing to keep in mind is when you get parallel lines, you should start thinking alternate interior angles, corresponding angles, and things like that. So what we end up having happen here is this angle is congruent to this angle. Those are corresponding angles. Over here we get this angle, put 2 marks here, is congruent to this angle. Okay? Those are corresponding angles. Or we could say like this angle and this angle are supplementary because they're consecutive interior angles. What we actually end up having, if I kind of cover this up, okay, the bottom up, we actually just get another trapezoid right here. Okay, so all the other things that applied to trapezoids would apply again to just kind of that top, it's not half, it's a little smaller than half, but that top section. Or if we look at it this way, right, just that would be another kind of really skinny, long trapezoid. Okay, so you could kind of reapply some of those things if you really wanted to, but you definitely need to know that mid-segment theorem. That's it for trapezoids. We'll come back with another video for isosceles trapezoids later.